In this lesson, we will consider another elementary circuit theorem known as the substitution theorem. Now, let us consider a circuit with some element. So, again this element could be nonlinear as well. Okay. And let us say it has some voltage V across it and some current I through it. Okay. Now, consider the following modification to the circuit. What I will do is, I will take the same circuit, okay, and across this element I will connect a current source like this and a current source like that, and I will choose the values of these current sources to be exactly I, where I is whatever current is flowing through the element V. Okay. Now, if I have two identical current sources connected in anti-parallel fashion like this, it is nothing, it is an open circuit, right. This is a zero valued current source. If I have this both being I and I, then this is equivalent to an open circuit, okay, because whatever current comes in here goes that way and goes that way. So, the current here is 0 as is the current over there. Okay. So, it is really an open circuit. So, all I am saying is I will connect an open circuit across the element, and obviously, that will not change anything in the circuit, okay, because I have this element, and to say that I connect an open circuit across it means that I have really not changed the circuit in any way. Okay. This is just a fancy convoluted way of showing an open circuit, but there is a point to it, as we will see. Now, keep in mind that the circuit is operating in some condition, right. It has some values of independent sources and so on, and the voltage across this happens to be V and the current through that happens to be I, and I choose the exact same current that is flowing through this, make two copies of it, connect them in anti-parallel across the element. So, clearly these two cases are identical to each other. That means that the voltage across this does not change, and not only that, you can have a number of nodes in the circuit. Okay. The voltage at any of them does not change. In fact, there will be no change at all through any branch voltage or any branch current in the circuit, because I have really not made any changes. I have just connected 0 current source across the element, and I have got a fancy way of getting this 0 current source. Okay. Now, let me take this and manipulate it further. What I will do is, I have these three elements in parallel. Okay. I have this element E, let me call it. It has a voltage V and a current I through it, and I have this current source this way and a current source that way. Okay. Obviously, this is a parallel connection, and it does not matter the order in which I show the parallel elements, because this is exactly equivalent to I, the element E with a voltage across it and a current I through it, and a current of value I. All I have done is, I have moved this here and I have moved this over there and I have moved this over there. I have simply redrawn it differently, that is all that is there to it. So, these are exactly identical. Okay. Now, I can redraw the complete circuit with this instead of that one. Okay. So, if I do that, this will change to this circuit where I draw the current source of value I first, then the element E with a voltage V across it and a current I through it, and the other current source I pointing upwards. Okay. Now, it is clear that there will be absolutely no change when you go from here to there. That means that all voltages will remain exactly the same. Okay, and all currents through all the elements will also remain exactly the same. Again, I have not really changed anything, I have just changed the way I have drawn the 3 parallel elements, that is all. Now, the interesting thing is that if you examine the current in this wire, what is it? The current in this wire is equal to the current flowing here minus the current flowing downwards through E. So, clearly the current in this link is exactly equal to 0. Similarly, the current in this wire is also exactly equal to 0. Okay. So, that comes from the fact that this element has a current I flowing downwards and this has a current I flowing upwards, and this current simply circulates here with 0 current through these wires. Now, the moment I know that I have 0 current through a wire, I can just cut it off, that is, I can turn it into an open circuit without altering the circuit at all, because after all it was carrying 0 current anyway. So, if I turn it into an open circuit, it will still carry 0 current and no circuit equation has changed as a result of this. So, the circuit conditions will remain exactly the same as before. Okay. So, what I am going to do is cut off these wires, okay, and I will be left with this. I. Okay. Now, if you recall, this is the same as the original circuit and this is the same as this circuit and this is the same as that circuit. When I say same, what I mean is all branch voltages and currents in the circuit are the same in this case and the original case. So, clearly it follows that if I have a circuit with an element E which has a certain voltage V across it and a certain current I through it, then the element E can be substituted by a current source of value I, where I is the current that is actually flowing through E in the circuit. Okay. I have to use that value of current, otherwise the whole thing does not hold, right. All my reasoning is dependent on the current source value here being exactly same as the current through the element E. Okay. I is the current flowing through E in the circuit. Okay. And this circuit and that circuit will have identical branch voltages and currents. Okay. Now, this idea that an element E can be replaced by a current source whose value equals the current flowing through the element in the original circuit is known as substitution theorem. Okay. An element E which has a current I flowing through it can be replaced by a current source of value I. Okay. And of course, the point is without altering branch voltages and currents, basically without changing the circuit conditions. Okay. So, that is the substitution theorem. I will illustrate it with an example. First, let me take an extremely simple example. Let us say I have 5 volts and 1 kilo ohm. Then clearly we know that 5 milliamp flows through this resistor. Now, let me substitute this resistor. What should I substitute it with? According to the theorem I just stated, I have to substitute it with a 5 milliamp current source. Okay. Now, what was the current originally flowing through the 5 volt source? It is 5 milliamps upwards, and in this case also it is 5 milliamps upwards, okay, in the voltage source. So, the circuit conditions have remained exactly the same. Of course, this is a very trivial example. Let me make it slightly more complicated. This is 5 volts and say this is 1 kilo ohm and this is 4 kilo ohm. And in this case, we will have 1 milliamp flowing through the whole circuit. And let me choose to substitute this 4 kilo ohm resistor. Okay. That means that I will retain the 5 volt source and 1 kilo ohm resistor, but I will substitute the 4 kilo ohm resistor with the current flowing through it, and I know that the current flowing through that is 1 milliampere. So, the current here is 1 milliamp. Okay. So, now let us calculate some quantities in the original circuit. This 1 milliamp circulates like this. So, there is a current in 5 volt source of 1 milliamp pointing upwards, and the voltage across this is 1 volt and the voltage across this is 4 volt. Now, let us go back to this circuit. We have 1 milliamp, which means that a current of 1 milliamp is circulating this way. So, the current through the 5 volt source is still 1 milliamp pointing upwards, the same as before, and this 1 milliamp is flowing through the 1 kilo ohm source. So, across this we will have a voltage drop of 1 volt, also the same as before, and finally, the resistance had a voltage of 4 volts across it. The current source which substituted the resistance also has 4 volts across it, okay, because 5 volts minus 1 volt is 4 volt. Okay. So, again nothing has changed. Now, I already proved it in the general case. These two cases are just for illustration. Now, this looks almost like a trivial theorem, and it is in some ways. It is very easy to understand. Its main value is in proving other theorems, and also sometimes it is useful for circuit synthesis. Okay. It turns out that you can also back substitute. In this case, in place of a resistor, I substituted a current source. Now, you can also go backwards. You can substitute a current source with a resistor subject to some conditions, and that helps in deriving new circuits, because sometimes it is more cumbersome to realize current sources, but you could in many cases realize the same functionality replacing the current source with a resistor. Okay.